Okay, this is your video for 6.1. 6.1 is about all kinds of polygons, and then the rest of chapter 6 is all about quadrilaterals, since we already spent so much time on triangles. But 6.1 is about all kinds of polygons. So the first thing we have on your vocabulary grid for polygons is, well, we actually talked about the definition of a polygon back in chapter 2. I'm sure you all remember. We said that there's a couple criteria. One, it has to be a closed figure with 3 or more sides, and the sides have to be straight lines. So those are basically the 3 criteria you're looking for: closed, straight lines, and 3 or more sides. And then here, if it is a diagonal, we have parts of a polygon here. A side of a polygon is the segment that connects 2 of the sides, so it just goes around the outside. Vertex are the points where 2 sides meet. And then a diagonal is any segment that connects 2 non-consecutive vertices. And by non-consecutive, we mean just not right next to each other. So from B to D is a diagonal, B to C is a side. B to E could also be a diagonal, or A to D, anywhere that goes across the figure. Polygons we can name by the number of sides, and you also have this in your chart, except for number 11 is missing. 11 is undecagon. So you know most of these: triangle, quadrilateral, pentagon, hexagon, heptagon. Don't get hexagon and heptagon mixed up. 11 and 12 kind of work like Spanish. If you take Spanish, 1 is uno. So 11 is undecagon, like 1 and then 10 would be 11. And 12 is dodecagon, so like dos decagon, 2, 10 would be 12. Anything higher than 12 we don't really call by numbers, we just call by the size. So 13 gon, 15 gon, 48 gon. So anything above that is higher. Okay, so the first example, we are going to just tell if it's a polygon or if it's not, and if it is, how many sides does it have. So this would be a polygon because it has the sides are straight lines, and it doesn't cross in the middle, it's not open, and so this means a polygon. And so we just count the sides: 1, 2, 3, 4, 5, 6. This has 6 sides, so it's a hexagon. Okay, this one, it's closed, the sides are all straight, nothing crosses or overlaps, there's no curves. So this is also a polygon. It looks a little funny, but it's still a polygon. 1, 2, 3, 4, 5, 6, 7. This has 7 sides, so this would be a heptagon. Okay, y'all pause and try C and D. Okay, C is not a polygon because its sides are curved, and because it only has 2 sides, so it has to be 3 sides of straight sides to be a polygon, so that is not one. D is also not a polygon because it's not closed. If I drew in a last side, or if I extended these until they met, either way that would make it a polygon, but because it was left hanging open, that is not considered a polygon. Okay, also from your vocabulary grid, we have whether it's regular or irregular. So from your vocabulary grid, if all the sides are congruent and all the angles are congruent, then it's an equiangular and equilateral polygon, and we call that regular. So if it's equilateral and equiangular, then we call it regular. If either of those is not true, then we say it's irregular. Okay, so we're going to classify by that here. So this one is equilateral, that's good, but it is not equiangular because these sides are congruent and these sides are congruent, but not all 4 sides are congruent. So it's equilateral but not equiangular, so we have to call that irregular. How about I learn how to spell and talk at the same time? That would be awesome. There we go. Irregular. Oh, we didn't talk about convex and concave. I'm silly. So convex means that everything points outward. Concave means that something is concaved in and it points towards the center. So concave is pointing in, convex is everything is pointing out. The way that the book defines it is by using the diagonals. In a convex polygon, all the diagonals are going to be completely inside the figure. In a concave polygon, you're going to be able to draw a diagonal somewhere that at least part of it is outside the figure. So this is the figure over here, and the diagonal is hanging around on the outside. So it's concave because these sides point inward instead of pointing out like it's supposed to. Okay, so this one, nothing is pointing inside. If I drew the diagonals, they would be inside the figure. So this is convex. Okay, B, this one is also going to be irregular because this is a very long side, this is a short side, and so this is a medium side. So it's not equilateral. It even is not equiangular. It looks like it is because they marked all these right angles, but look at this guy. He's an angle inside the triangle, and he's a big guy. He's bigger than 180. So this is not going to make it regular. So it's irregular, and it is concave because these sides point inward. And if I drew the diagonal from here to here, it would be outside the figure. So that is going to be irregular. Okay, y'all pause and try C and D. C is regular convex. It's regular because it's equilateral and equiangular. And it's convex because the diagonals would be fully inside the figure. D is also regular. We can see it's equilateral and equiangular. It is also convex. Now, one thing that maybe you notice from looking at these is if you're regular, you have to be concave. There's no way you can be regular concave. Because of these, you would have these big giant angles like this. So even if you had, I don't even know what I'm going to draw here. Even if you had something like this and all the sides were congruent, it could never be equiangular as well because you're always going to have the big angles that are more than 180. So it's never going to work. So anytime you put irregular, you can just go ahead and automatically put, anytime you put regular, you can automatically put convex. Irregular can go either way, but regular has to be convex. Okay, moving on. Oh, nothing to hide on this page. Okay, you have this on your vocabulary grid where we can figure out how many angles are in each polygon. And we do that based on a triangle. So we already know a triangle has 3 sides. There's one triangle, and we know a triangle has to add up to 180. We have a quadrilateral, and if we draw in one of the diagonals, you can see that the quadrilateral turns into 2 triangles. So that would be 180 degrees here, 180 degrees here. So a quadrilateral has 360 degrees. A pentagon, if you draw 2 diagonals, oh, that didn't work. If you draw 2 diagonals coming from the same point, that forms 3 triangles. So that would be 180, 180, 180. So a pentagon has 540 degrees. A hexagon, if you draw all the diagonals from the same vertex, that would cut this hexagon into 4 triangles. So that would be 180, 180, 180, 180, and that would be 720. So you can get this pattern that emerges here. However many sides there are, there's always 2 less triangles than that. So 3 sides make 1 triangle. 4 sides make 2 triangles. So this is why we have n minus 2 here. And then you just multiply that by 180 to see how many degrees there are in the entire figure. So what we get out of this is this theorem here for 6.1. It's called the polygon angle sum theorem. And it says the sum of the interior angle measures of any convex polygon, this only works with convex, is 180 times n minus 2. Okay, so that's what we're going to use for the next couple of examples. Alright, so find the sum of the interior angle measures of a convex heptagon. So heptagon has 7 sides. So we're going to plug that into our formula. So if it has 7 sides, that means it has 5 triangles when I draw those in. And then I know there are 180 degrees in each triangle. So that means a heptagon has 900 total degrees in it. Okay, B, find the measure of each interior angle of a regular 16gon. So this one's a little different. It wants to know each individual angle instead of all added together. That just means it's one more step. We're still going to do the 180 times n minus 2. So n is 16 this time because it's a 16 gon. And you can do this individually, or you can type this all in at the same time. 180 times 16 minus 2. So a 16 gon has 2,520 degrees total in it. But I want to know about the each angle. So we know if it has 16 sides, that means it has 16 angles in it. And if it is a regular 16 gon, then it's got to be equiangular. So each of those angles has to be the exact same measure. So I can just take this and divide it by 16. And I know that each of those individual angles, is 157.5 degrees. They all have to add up to 2,520. They all have to be the same because it's equiangular, so they're each going to be that much. Okay, C is kind of the same thing, but with a little bit of algebra. Find the measure of each interior angle of a pentagon ABCDE. So the first thing I want to do is I'm going to add all of these up to see how much they add up to. So I'm going to say 32 plus 32 plus 18 plus 35 plus 18. In total, that means there are 135 C in this equation. Then I'm going to do my 180 times n minus 2. And I know either from your chart or from doing this formula that a pentagon has 540 degrees. So I'm going to solve for C. 40. So I know that C is equal to 4. So then it says find the measure of each interior angle. So I can just go and plug that back in. 34 times 2 is 128. 18 times 4 is 72. 72 degrees. And 35 times 4 is 140. Then I could go back and I could check. I could re-add all these up and make sure it adds up to 540. Okay, so this is the same formula looked at 3 different ways. One time, what's the total angle? One time, how much is each angle in a regular, however many gon? And then the other one with a little bit of algebra, so you write an equation and work. So 3 different ways to work out 3 different applications of the same thing. Okay, so let's switch over and let's talk about the exterior angles here. So we have 2 examples. Here we have a triangle, and I have 3 different exterior angles, 81, 132, and 147, and they add up to 360 degrees when I combine those. Then, 1, 2, 3, 4, 5, I have a pentagon, and I have all the exterior angles shown, and all of those add up to 360. So from there, we can kind of conclude the polygon exterior angle sum theorem says the exterior angles add up to 360, no matter what. No matter if it's a triangle or a 57 gon, they're always going to add up to 360. So interior angles, you have to do the little formula, the 180 minus 2, 180 times n minus 2. For exterior angles, it's just always 360 no matter what. Okay, so let's look at some applications of that. Alright, so this one says find the measure of each exterior angle of a regular 20 gon. So we know in any regular anything that there are 360 degrees total. We know if it's regular, then that means that it's an equiangular figure. So we know all 20 of those angles have to be exactly the same. So we can divide by 20 and get our answer very easily. And it is 18 degrees. Good. So that one's very similar to this last example that we did here where we had a regular 16 gon, so we divided by 16. Only I didn't have to do the formula. I could just use the 360 because I am talking about exterior angles. Okay, B is very similar to example C from the last one. I'm going to follow the same procedure. I'm going to add all of these up. So I'm going to do 33 plus 16 plus 10 plus 28 plus 15 plus 18 plus 33. Oh, wait, I started with 33, didn't I? Oh, my goodness. Okay, so that means I have 120 B's. They're all exterior angles, so I know they have to add up to 360. I'm like not doing any math in my head today. So I know that B has to equal 3. And you could go around and plug that back in and add those up and make sure they add up to 360. But they're asking for B, so there's no need to go and plug it back in this one. Okay? All right, example 5. Anne is making paper stars for party decorations. What is the measure of angle 1? And angle 1 is this little thing out here. So there's 2 ways that you can do this. You know that the center of this is a regular pentagon in here. So I can either find the measure of an interior angle of a polygon and then do linear pair theorem. That would work, but that would be several steps. One thing that would be easier is if I just use my exterior angle theorem that I just learned. So I know the exterior angles of a pentagon are 360 degrees. I know that they all have to be the same. So I can just do 360 divided by 5. And I can say each one of those is going to be 72 degrees. Okay, y'all pause and try B for yourself. Okay, B is the exact same thing, only this is a decagon because it has 10 blades. I don't know if y'all can see your picture better than mine, but we are talking about an exterior angle. So exterior angles always add up to 360. There are 10 sides, so I'm just going to divide by 10. So X is equal to 38. So tomorrow when you come to class, your 6.1 vocabulary grid is due and these notes are due. See you tomorrow.